Hey everyone, it's Mr. Thrasher. I hope you had a nice spring break. We're still talking about light. As a reminder, we've learned about waves, including like wavelength and period and frequency, also how waves interfere and interact with one another. We're talking about light. After we discussed sound, we started looking at light, and hopefully, if you remember from our week before spring break, we saw that light behaves like, well, a wave. Now, unfortunately, that's actually not the end of our story. We're still trying to learn this week what exactly is light, because that's the basis of this unit, how to send and receive and view a snap. So, we saw that light has very wave-like properties. Let's remind ourselves about waves and particles and understand this. This is the end result of this video, something known as wave-particle duality. Okay? First, particles. And when I say particles, I mean stuff with like mass, right? Think of the stuff around you, from a rubber ball to like a little Nerf dart, a microwave, a couch, a bed, a house, right? A whole building. These are particles, things that are made of mass, things that are made of like atoms. We know how matter behaves. And even if you've never taken a physics class, right, we have a lot of intuitive sense. Our scale, our environment is all about particles behaving. And I have just right here some bullet points of how particles, things with mass, behave. For example, we learned about this earlier. We know that we can relate the energy of a particle to like how fast it's moving, right? Think of kinetic energy. We also know that while there can be big things and little things, big particles, big objects and little objects, they're more or less localized, right? If I said, where's the ball? You would say, oh, it's right there. The couch is over there. They're in one given area, one given location in space. Also, we know pretty well how particles interact with one another, and we studied this, right, when we were doing momentum. If I have two particles and I slam them into each other, they have some type of collision. Maybe they stick together, maybe they bounce off. We know that a lot of times energy is not conserved, but a lot of times momentum is conserved. We can study and describe that behavior. And then, oh my gosh, especially last week, we learned about this other thing. After learning about particles, we learned about waves. And waves seem to behave, and they seem to be quite different things, right? A wave is, while particles might vibrate up and down, waves are a transfer of energy from one location to another. And the way that waves interact is quite different from the way that particles interact. Remember, from interference, those waves kind of add up, and that's very different than particles. Particles don't really add up when they collide. But also, as I really tried to stress, after that interaction, that interference, waves keep on moving. Okay, so we have these kind of two different things. We have particles and stuff that we can put into the category of particles, okay, like everyday matter. And we have waves and things that we can put into the category of waves. And then we were looking at how sound was a wave. We were looking at light as a wave. We watched this video and we saw that when you have these interfering waves, by looking at how they interact, do you have like bright spots and dim spots, or loud spots and quiet spots? That's a way to prove whether or not something is acting as a particle or a wave. And that's really how we proved by the end of last week, or at least before we went on spring break, that light in fact is a wave because it has this interaction. I want to show you a video. It's going to happen pretty quick. It's called an interferometer, and it's another way to show that light has these wave-like properties. It seems a pretty convincing experiment to show that light is a wave. And what you have here is, this is like a laser, and it's going to shine a laser light, and that light hits this, and it's going to get split. Okay, kind of like half the light will go this way and the other half of the light goes this way. So let's watch. Here comes the light. Okay, it splits. Half of it goes here, right? There's the wave. This is like a mirror. It's going to hit the mirror and it just reflects right back. Okay, the light reflects, it comes back, and then this also is kind of going to recombine. The light reconvenes, and then it's going to get shined over here. And this is almost like a film, or like, think of like an X-ray film, and we can see what's going on with the light. And again, the wave was also sent this way. And here's what the video is showing right here. We see that sometimes this light and this light from over here, sometimes there's constructive interference and sometimes there's destructive. And remember from our activity, that leads to the brightness getting dim or bright, dim or bright. And you can change that effect, whether it's bright or whether it's dim. Sorry, I kind of went a little slow as that video was going. By changing this distance, if you make this mirror further away, it's going to change how these are lined up. And this interferometer is used a lot in science. We use it to study both things like light, things like distances. You can actually use this to measure distances. And it's all about using the wave property of light. So just like those double slits from the week before spring break, this is another classic experiment. We could actually have done this in our classroom to show that light has wave-like properties. So that seemed to be kind of the end of the story. Okay, there was kind of a debate whether light was a particle or wave. Isaac Newton actually thought it was a particle. Okay, but then after we did this experiment with the double slits, and scientists also built this thing known as an interferometer, oh my gosh, seemed to put the nail in the coffin. Clearly light's behaving like a wave because it has interference. And that was kind of the end of the story until the early 1900s. And oh my gosh, we're back to Einstein. Einstein did an experiment. He was studying light and the effects of light. And after doing a physical experiment and then deriving a theory, really a mathematical application of physics equations and laws, he came up with something known as the photoelectric effect. And when that happened, there was a problem with the wave theory of light. Einstein had something to add because it turned out it's not quite as simple. And I want to show you this photoelectric effect quickly. Okay, here I have a flashlight. And what it does is it shines light. And I can shine like red light. I could go like over here, shine some red light. Or I could shine green light or blue light. I could also shine like ultraviolet light. Okay, and if you remember, like this is low energy red light and this is higher energy blue. Ultraviolet has more energy, that's why you get sunburns. And right here, this is a funny looking contraption. Essentially, I have like wires here, wire, and I have a battery. And the battery is so I have like a negative charge on one side, a positive charge on the other. And right here, I have just a piece of metal. It says zinc right here. This is a piece of zinc. This is what Einstein found out. If you take a piece of metal and then all of a sudden you start shining a flashlight on it, okay, and let's say we're using an ultraviolet flashlight. Okay, let's see, let's go. Oh, I got to hit the play button, excuse me. So I'm shining some ultraviolet. These right here are electrons. What Einstein figured out is if you're shining light on a piece of metal, the electrons, some of the electrons in the metal are getting knocked off. And I don't mean like they're vibrating back and forth, like we know that particles on like a string will vibrate when a wave comes by. These particles, it's like they're getting knocked off of the metal. And this is a very weird interaction if light was a wave. Again, waves, they don't knock things off. They don't interact like two balls interacting, like billiard balls. But Einstein found out that when light is hitting this metal, the light is imparting momentum. It's imparting kinetic energy. And that is not how waves are described. He also found another interesting bit was that obviously, like if I have this light and I increase the intensity, like the brightness of the light, it's ultraviolet. You can't actually see ultraviolet. But if I have more intense light, imagine like 30 light bulbs, it looks like you get more electrons being kicked off. That's maybe not surprising. But what Einstein found out, and this is really the nail in the coffin for the classic wave properties of light, at least to the extent we're going to get into, if instead of ultraviolet, if instead Einstein shined blue light, nothing. Even if we waited a day, a week, a month, 10 years, even if all this energy, all these vibrations from blue light, they never have enough energy to knock loose an electron. And to be honest, even if we crank up the intensity, blue light simply doesn't have enough energy. Whereas even if you have just a little bit of ultraviolet, you start knocking loose electrons. Again, this does not describe how we know the energy of waves behave. So Einstein, and then later on some of his contemporaries, okay, de Broglie, they started deriving equations that really show that light behaves, oh my gosh, not like a wave, like a particle. So oops, I went too far. Here is another diagram of this photoelectric effect. If you want to know where do we see photoelectric effects, this idea of electrons or light coming in and knocking loose electrons, that's what solar panels do. We never actually studied solar panels when we were studying power plants because they work on a very different mechanism. They are based on this idea that if you have high enough energy light, and if you have the right material like sunlight can have enough energy, the sunlight comes in, it knocks loose electrons, and these electrons can create a current. Okay, but this idea of imparting energy, imparting momentum, oh my gosh, this does not match our understanding of how waves behave. It's a very particle-like interaction that's going on. So after all of that, we looked at how light is very much like a wave before spring break. Now Einstein found out that waves are in fact like particles, and subsequent experiments and theoretical approaches show that light often interacts like a particle. So what's the answer? Is it a wave or is it a particle? And here's the problem. We've been looking at this the wrong way. It's not that you either have waves or particles. It's that actually, and this is weird and not intuitive, things act like both waves and particles. And this is a good example here. If you had scientists with blindfolds on and you had something that's pretty complicated like an elephant, depending on where the scientist was looking, feeling, they might describe different things. It's similar for light. Light's pretty complicated. It is both. It has both tusks and tails. It both exhibits wave particles or wave properties and particle properties. It both interacts with momentum and kinetic energy like particles do, and it has interference like waves do. And that's tough because most of the stuff around us doesn't act like us, like that, I should say. Okay, you have to look at really small scales to see the particle properties of light, and also you need to look at very large scales to see wave properties of matter. So light is not a wave or a particle, it's a wave particle. And this is the most interesting thing, and maybe the most mind-boggling thing. This is true with everything. Everything actually has wave properties and particle properties. That's this last bullet point right here. Oops, that should go away. Okay, you have wave properties. The baseball that's maybe in your room has wave-like properties, and that's very weird. But those wave-like properties of a baseball, they're not on our scale. You don't think of like interfering baseballs. Even though it does have a wave property, it's at a scale incredibly, incredibly small, those wavelengths. To see like interference patterns for baseballs, you need incredibly large scales. So light is both a wave and a particle, and while we won't spend a whole lot of time on this, in fact, everything has wave and particle properties. Real quick, one example. I know I'm at 12 minutes. I'm going to try and go quick. If I took a gun that fired electrons, and I had this wall that had 2 slits into it, well, it probably wouldn't be unreasonable for you to think that, well, these electrons, they are either going to go through this hole in the wall or this hole or slit in the wall. They're going to look like this or like this. But scientists do this experiment. And so I'm not firing waves, I'm firing particles, electrons, right? But when scientists do this experiment, they don't see this. They see this. They see that when you fire electrons, particles, at 2 different slits, you get an interference pattern. This is a proof to show that it's not just waves or it's not just light that has particle and wave properties. Even things that we would classically call particles, objects, things with mass, electrons, are both waves and particles at the same time. In fact, you could even do this setup with like baseballs or with kittens, right? I could get a kitten cannon and fire cats, and if this distance is far enough away, I would see an interference pattern of cats against the wall. It turns out this distance you would need for cats, right, or like baseballs, is quadrillion of light years, almost larger, in fact, larger than our observable universe. So again, things on our scale, it's very tough to see these kind of wave properties, but it turns out it does exist. So light is really both waves and particles, and in fact, all particles have wave properties, all waves have particle properties. To be honest, in this class, we are going to focus mostly on the wave aspect, but there will be times when understanding the particle-like properties of light is important. I apologize, this video is a little longer than my normal ones, or at least the goal I try to have. Thanks a lot for watching.